All right, record is rolling. We're back from outside in the lab. You guys have your data, so I will take you guys through the process to solve for the spring constant. So everybody has the either 9.8 or 2 meters per second squared here. 2 meters per second squared. I was going to use that. Now, a lot of you guys used the full height of the balcony, which was it was about 4 meters. You may have gotten a little over 4 meters. I'll just call it even 4. How about that? Right. But if you got something a little different, you got like 4.1, 4.2, go ahead and use that number there. Right. But just take it. All right. So one of the landing points, that's all Harry measured like 9.3 meters. So here, I'll go ahead and use that. I'll use 9.3 meters. All right. But you guys got different values that you measured with the meter stick. So whatever you got, you can just write under for D, right? How many meters out it went. That's probably about a reasonable number that you could have gotten, or so pretty close to that. How many meters? Okay. Right, you guys good so far? Right. Now the time of fall. Now the time of fall has something to do with this 4 meter height drop. Right. So here's where we need to do calculations. Calculation time. Isn't the height of fall equal to 1/2 GT squared? Okay. Hey, do you remember that old Paul Hewitt story? Walking to a mine shaft. That rock fell for 5 seconds. 5 times 5 times half a 10. It's about 125 meters deep. College, you guys remember that? Hey, that's that equation. Only now just the numbers are different. And also we're solving for t instead of 8. So you know what the height of fall is. It fell so many meters, right? Maybe that many meters. You know the of course we're on Earth, so I'll put in 10 meters per second squared that it was accelerating downward. Right? And we're trying to figure out, what was the time of fall? Now, I know that on Earth, if you drop a rock from the edge of a cliff and let it fall for 1 second, it will fall 5 meters, right? 5 meters in 1 second. So the fact that it fell 4 meters means that this time should be a little bit less than 1 second. So if you do the calculations correctly, you should give it a little bit less than 1 second. So I know half of 10 is 5. I can divide the 5 down. What would it be? 4 meters divided by half of 10 is 5. Divide that down here. The unit also divides down is equal to times squared, right? So should it just be the square root of this expression? Oh, it looks like the meter's getting canceled. Second squares comes back up on top. So time is equal to, it's going to be a square root. I got 4/5, and 1 over second squared is like second squared, which is inside the square root. So it's gonna bring us back to seconds. Right, you see that? Right. So what is the square root of 4/5? We got 0.89. Hey, remember I said it should be a little bit less than 1 second? Like the unit for this is seconds. That is a little bit less than a second, isn't it? Look at there, look at there. So we're getting a time of 0.89 seconds. Say 0.8944. No, okay. Probably say that. That's probably about as much precision as I can get though. Okay, you guys get? All right, so back to the table. Right, so we just calculated this. Okay, some of these are measurements, some of these are calculations. Okay. This is 0.89, and the unit, which I typed for you guys is wrote for you guys is seconds. Okay. I should emphasize where these numbers are coming from. So we're treating free fall gravity as a given. You guys measured the height change. You guys measured the horizontal displacement of the ball. You spotted the ball. Okay. We just calculated the time of fall. Okay. We're also about to calculate the blast speed. Right? You had to do the time of fall first, but we just got that. So now we can calculate blast speed. Now this is projectile physics. Right? This is just this right here, right? You guys remember? Right? So if the ball goes this horizontal displacement in this fall time, then you have enough information to calculate the blast speed, right? That's what we're about to do right here. So we're going to do the setup. Horizontal displacement is equal to v blast times time of fall. Okay. We're going to plug in here. Okay, use this measurement, 9.3 meters, which you may or may not have, but that would be a reasonable number because I know at least one team has that, 9.3 meters. We're seeing what's the horizontal component of velocity, which of course is the blast speed because you aim the blaster horizontally. Okay. And the time of fall, we just calculated that. Based on the height drop, we got 0.89 seconds. Right? So does it go right there? 0.89 in the unit of seconds. Is that? Hey, if I take the number of seconds and divide it over, wouldn't that be so many meters divided by so many seconds, which would describe a speed, a blast speed. The blast is whatever 9.3 meters and 0.89 seconds is. Let's see, 9.3 meters and 0.89 seconds. I'm looking at 10.4 meters per second. Yeah, that number looks reasonable. 10.4 meters per second, I can believe that. Oh, okay, yeah, thank you. All right, so that then is that's somewhere between 20 and 30 miles an hour. Somewhere there. Yeah, that looks about right. Okay, you guys good so far? Right. Now, back to the projectile lab days, I think that was our goal back in the day, but we're gonna go an extra step here. So let me write this in 10.4 meters per second. Okay. Oh, there's this last measurement you had to get. So this column is measure. Right, and then the last one will be a calculation. Okay. So how much did you compress this blaster? Right. So I will do a live demo right here. Gotta figure this out. Okay. So this ramrod feeds just that far into the launcher right there. Make a little mark. Okay. Yeah. Yeah, go ahead. No, Harrison, since these are your numbers, did you go 1, 2, 3 clicks? Did you do all 3 clicks?
Yeah, I'll do all the way.
All right, all the way. Let's do all the way the same thing. All right, so go that far. Takes us right to there, like right to the edge of the fuzzy thing. Okay. So what's the difference? That difference is it looks like 7 centimeters. 7 centimeters. Okay. So am I gonna write x is equal to 7 meters? Is that what I'm gonna do? 7 meters? No, that's like a multi-story building. I'm going to put 0.07, right? Isn't that 7 centimeters? Right? You want to throw in another 0? Good, I guess. Okay. And last step, what is the spring constant? Okay, now here's the conservation of energy application. Okay, so we're doing initial to final setup, right? Point A, point B, initial to final. Okay. So at one point, the spring was spring loaded, 1/2 kx squared worth of energy. And at one point, that all went into, well, kinetic energy, 1/2 mv squared. Right. So that's my entire setup right there. Okay. So let's break out need more paper. So we're doing sum of energy initial equals sum of energy final. All the energy was in the spring, 1/2 kx squared. Solid for K. And then right when I left launcher, it went all to kinetic, 1/2 mv squared. Okay. And out of these 4 variables, point, we have 3 of those by this point. Right. So let's just plug this in. 1/2, here, solid for K. Okay. The X, the spring compression, I just measured that at 7 centimeters. So I'm going to call that 0.07 meters. That's being squared. Okay. That's equal to okay, so this spring potential energy is equal to this kinetic energy. The mass of the ball, now the mass of the ball, I went ahead and did this morning before you guys came and spoke. I got 6.4 grams. So we're going to call that 0.0064 kilograms. Right? Just like that. Okay. Right. And then the blast speed. Now the blast speed, that's where the projectile physics kicks in. Remember we got 10.4 meters per second? Well, at least that's definitely true for one team. And then that should be a reasonable number. I bet you guys all have a blast speed that's pretty close to that, right? And don't forget to square the blast speed, right? Is that true? Just like that? You guys okay with that setup? Right. All right, so we're going in for the win here. We're just a couple algebra steps away. Right. I can cancel out the 1/2 on both sides. Okay. And then take this 0.07 meters squared and divide that down. Is that? So K, the spring constant, is going to be the mass of the ball in kilograms times the blast speed in meters per second being squared, all divided by the compression of the spring in meters, also being squared. Right, just like that. Right. All right, so and this will naturally come out to some number of Newton per meter. Right. Now I'm gonna make a guess before I chug all the stuff. My AP class earlier today was getting somewhere between like 100 and 200 Newton per meter. That sounds about the correct order of magnitude. So it's probably going to be somewhere in that ballpark, about 100, 200 Newton per meter. Let's see. Let's find out because I don't actually know. 0.0064 times 10.4 squared divided by 0.07 squared. All right. Yeah, 141. Look at that. 141 Newton per meter. So K is equal to 141 Newton per meter. And that is the answer to the lab. Okay. All right, so finish this page. I'm going to go under K, write 141 Newton per meter, and good to go. All right, you guys got that? Okay. Oh, all right. So, tell you guys what. I need to get this page from you guys. Yeah, guys, turn this page in at some point because it's got a couple of labs on it. All right, if you want to hold on to this page for a couple of days, here tomorrow I'm going to get you guys your quiz. Okay, right, tomorrow I'll get you guys your take-home quiz. All right. Actually, you know what? Change your mind. I'll give it to you right now. I'm going to get you guys your take-home quiz where there's just a couple minutes till the end of class, and then I mean, if you got the conceptual questions, it's gonna be open notes. You can do this. Right. Can you guys turn this lab either today or by the end of the week? Can you guys see that? Okay, so you guys are gonna turn in this page either today or by the end of the week, right? And I'll get you guys your take-home quiz right now. So if you just want to knock out these questions, which you have the answers to, then you can do that. All right, so let me go ahead and end this recording, and that is a wrap on today. And again, all I'm doing is I'm about to pass you guys out this here take-home quiz.